I hope you don't mind that since you're not taking notes, we're really whipping through this. It's okay? Right? We should actually one day do everything on the board and see. I've done this before. I've taught this class like on the board. It takes the full 3 hours to get all of it up on the board. I mean, it takes me much more than that to get all these on the slides because I make mistakes in my calculations too. But the nice thing about doing it on here is I can delete the entire slide. So homework, I assigned you 3.1, 3.2, and 3.4. And I went through some of them, and they are difficult because they're coming from this book. So I would just like you to try them, and don't get stressed if you can't get through them. Just do your best to try it, because some of what's going to happen is that you're going to get hung up sometimes on how the C1 and C2, or there's going to be a C3 there, right? They're all going to get hung up with each other, and you're not going to be able to isolate them properly. So it's a little confusing. And I also think in these sections, and I started this one, you'll see what I mean by hung up. I just wanted to start it off and show you. But I don't think he wants the general solution. Because if you look up to this section where he lists these problems, he doesn't ever talk about the general solution. He's just looking at one solution. So that makes it a little bit easier. If you go back and look at his examples, he has a few examples right before this section. It's exactly that. So again, it's, if you have a function like this, what are you looking for? You're looking for a family, not just one function, but you're looking for the family. But I don't think he's really looking for the family. And so you set up the equations so that that's the same. You look at the relationships, you integrate, and you get the C1. You get the U equals C2 like before. And in fact, this one works out okay, I think, 3.1c. And then you can check by just taking the derivatives and punching them into the equation. And it works out just fine. That was 20 minutes of board work. Think about it, right? You all teach, you know that this is about 20 minutes of board work right here. Have I got better at this since algebra?
I think so.
Yeah, it took me a long time. Bill was saying that other people should do this too, and then we could get some courses online. It took me, I think, a good 6 years to get the handle of doing this right. But okay, this is the one that gave me some trouble. So I'll show you how it gets kind of tangled. It's just it's messy. So you're seeking a solution, our family solutions, but now you have 3 independent variables. You have now 4 equations coming down the line. I mean, it's not impossible. It's just the problem is you have to solve it in such a way so that you isolate one of the variables so you can get your hands on it. You don't want to work with a system of nonlinear ODEs because then it gets awful. So you have this, and du dx equals 0. And I say what a mess, you don't see the mess sitting there, but if you start looking at thinking, how are you going to get the y and the x to have equations with only y and x's in it? You have a z in it, and the z is hooked up there, and this is not linear, so you're not able to pull a solution from this, and there's no technique for it. So there's some trick, substitution trick, where you can keep playing with it and get it out of there. So it's going to take some thought, and I did play around with it for a while, and I thought, okay, I'm going to drop this, but I'm going to let you guys know that you might get hung up like that. So don't get too frustrated. It's algebra. I'm going to show you one trick that helps, and that's instead of writing them this way, recall that I originally wrote the equations this way as in parametric form with the dx dt before I did all that. So you can put them back in parametric form. And what made me think of doing this is this one's decoupled from the other two. So this allows you to get a solution for the dy dt. So these are the parametric versions of the characteristic equations. That gives you an advantage in the fact that you're able to get a solution for y, but now you have a parameterized t that you somehow need to get out of there. So even though you have that solution, you can substitute them back, and then you're going to get what we call non-autonomous differential equations. And I'm just showing you where I went with this. It's not very nice. So if you take the y equals c1 e to the t and substitute it into this equation, then you get dx dt is equal to c1 e to the t plus z, and you get dz dt is x minus c1 e to the t. Doesn't have to be the path you take, this is the path I took. I got the second things in terms of the second derivative, and I arrive at x double prime equals x. Now that equation, in a differential equations class, you guys talk about that. Actually, I think you might talk about second order linear equations towards the end of the class. Yeah, I think it is, because you need, with second order linear equations, you need to look at things like the eigenvalues, right? So, and sometimes you get the center, you get all kinds of weird things happening with it. It's not trivial. So just to remind you, and if you haven't seen it before, what you do is you solve for the eigenvalues, and you actually can put this thing in matrix form, and it becomes a matrix, and it's the same thing as looking at the eigenvalues of the matrix. But the way we do it is we substitute lambda squared in for the x double prime, and you put in lambda for the x primes, there are none here, and then you put 1 in for the x. Yep, for the eigenvalues. And then, once you get the eigenvalues, then you get a linear combination of e to the t and e to the minus t, e to the lambda I, a lambda t, and e to the minus lambda t. And this actually, what you're doing is a spectral expansion of the matrix that you get by making this into vector form. And maybe next time I'll show you that. It's not that important actually for this class, but there's a connection to linear algebra. It's not a different eigenvalue, it's the same eigenvalue. So it's starting to look pretty scary, because now I have all kinds of constants floating around. I still have to get rid of my t. My t is not supposed to be there. I'm supposed to get y's and x's and z's and some constants. So it's starting to look pretty scary. It doesn't look scary maybe from where I left it off, but yeah, I'm looking at it going, look, I've got 2 constants. I'm not supposed to have 2 there, I'm supposed to have 1. And I have a t floating around somewhere. I think I got rid of the t. I figured out a way to get rid of the t by substituting, yeah, so I dealt with the t right away. But I'm going to get into more scary stuff, because I'm going to take this and put it back to the z equation. So it's definitely not trivial. You know, we're going to keep going, but you're going to get a function of 2 variables in this case, and it's a little messy. So let's take a step back and go to some of his simpler examples. So this was one of the problems in the book. Let's go to one of the simpler examples and see how he deals with 3-dimensional simple examples. In this example, you have, again, x, y's, and z's, but you have nice things on the bottom. And we only get really one equation, dy dx equals 0, y is a constant, and dz dx is equal to 0, so z is a constant, and du dx is equal to 0, so u is a constant. And so you get that C3 is f of yz, which means that all of your solutions, it's any function of y and z will work. Check it, ux is 0. The other 2 can be anything you want. Plug it into the equation, it all wipes out in 0. It's one of those things where it's so easy that it's confusing. Like I like to ask in Calc 2, integrate 0 dx. Always trips them up. Ask him to graph sine of pi over 2. You can see that outcome, right? Okay, any questions so far? It's a procedure. You follow the procedure. It's just that the algebra and the calculus can get scary.